In today's episode, we're going to look at equations of value, and in particular their context in simple interest calculations. So, we already know that this concept of money has time value. And so, what does that mean? It means that in the mathematics of finance, we're dealing with dated values of money. We're trying to compare a sum value, x1, at some time, to some other value, x2, at some other time. So, how do we compare them mathematically? Well, we can compare dated values of money by the following definition of equivalence. At a given simple interest rate, R per period, X dollars due on a given date is equivalent to Y dollars due T periods later if any one of the following is true. Either Y is equal to X accumulated by the factor 1 plus RT, or equivalently we could say that dx is discounted by, or the value of Y discounted by the factor 1 plus RT. Now, it's perhaps best to represent this diagrammatically. So say, for example, we have X at a given date, some date now. Then at a later date, specifically T periods later, the equivalent amount of money would be X1 plus RT. Or, perhaps in the opposite direction, at an earlier date, we could also say the equivalent amount is X1 plus RT using a negative 1, so we've discounted it by that factor. Let's have a look at this in the context of an example. A debt of $3,000 is due at the end of 6 months. So we're standing at time 0, and now we're 6 months into the future. We've got a debt due of $3,000. Find an equivalent debt at a simple interest rate of 8% per annum at the end of 3 months and at the end of 1 year. So let's first draw a diagram of the situation here. So what we have is our $3,000 payment at time 6. We have one possible payment, which is at time 3 months. And then we also have the other payment due in 1 year's time, or the other possible replacement payment due in 12 months' time, or equivalently 1 year's time, labeled at X2. So the first thing that we're going to have to do is we're going to have to find the amount of time, or the difference in time between X1 and the $3,000, which is simply 3 months. Note 3 months, or 3 out of 12 years. Again, we're dealing with an interest rate percentage per annum. And because we're dealing with a per annum percentage, we've got to convert any amounts of time, 3 months, we've got to convert that to years, 3 out of 12 years. Or equivalently, we've also got the X2, which is occurring 6 months later into the future, or 6 out of 12 years into the future. So to calculate our value of X1, what we've done is we've taken our $3,000, we've discounted it, notice because we've taken it to the power of negative 1, that's some date earlier in time, and we've discounted that and using the factor 1 plus R, which is our 0.08 or 8%, and then we've got our T here, which is the 3 on 12, again 3 on 12, not 3, and that gives us a value of 2941.18. Equivalently, we could do X2, and X2 is the $3,000, but now accumulated by the factor 1 plus R times T, where now T is our 6 on 12, and that gives us a value of 3120. So we've had a look at how to replace one payment, but actually in general we're going to be interested in replacing a set of payments. So let's go to the next slide. Another key element of financial mathematics, like I said before, is replacing a given set of payments with an equivalent payment at a particular date. We say that two sets of payments are equivalent at a simple interest rate if the discounted values on these sets on any common date are equal. This common date is called the focal date or the valuation date. So here's a nice linguistic definition of what equivalent sets of payments are, but for the purposes of demonstration, I'm going to try to formalize this with some mathematical notation. So, say we have payments x1, x2, up to xn. In other words, we have n individual payments occurring, say, at times t1, t2, tn, where ti is an element of R. So here I've drawn a diagram of this situation occurring, where we've got x1 here at time t1, x2 at time t2, and so forth up to xn at time tn. Now, notice I have specified that ti is an element of R, not simply ti is greater than or equal to 0. I haven't placed a zero, a boundary or a lower bound of 0 on our time. And the reason simply for this is in the context of a question, say, for example, say we're sitting at time t equals 0, or we're sitting at, I should say, the present date. And then say, for example, we have a payment that occurred previous to the present date, then that is technically at a negative time. Although we're not necessarily familiar with this concept of negative time, certainly in physics and other sorts of areas, we typically say that the constraint is that time is always greater than 0. But in this particular instance, we're going to say, well, we can have past values, we can have sums that get paid at past dates, and therefore we can have negative values. We're not going to have a look at an example of negative values, but for the purposes of this understanding, we can have negative values from a conceptual point of view, which represents time less than 0. Now, we've also got this value here, capital T, and capital T is what I'm going to call the focal date or the valuation date. Now, in other words, what we're going to do, in some sense, is to find the value of these payments. We're effectively going to treat them as individual payments first. We're going to accumulate them or discount them, depending on whether they occur in the future or in the past. We're going to bring them to a value at time t, and then we're going to sum them together. So, in some sense, what we're going in if we were to look at x1, say, for example, if we were to we see that occurs at time t1. T1 is sometime in the past compared to the valuation date t. So what we have to do is we'd have to accumulate to time t using a simple interest rate of R, so on and so forth. And the opposite can be said of xn, where xn is sometime in the future. Tn is sometime in the future, and so we'd have to discount our value xn back to the valuation date t. So to do that, let's define a few things first. So we're going to introduce this concept of the sine function. So broadly speaking, the sine function, sine of a value, takes 1 when that value is positive, and whatever's inside the brackets, it becomes -1 if what's in the brackets is negative. Hence, it's the sine function. It simply determines whether a number is positive or negative. So in the case where, say, for example, ti is greater than t, so in the diagram, this is, in this case, tn is greater than t, or tn minus 1 for that matter, and so on and so forth. So in those cases, what we have is that the sine of t minus ti is actually equal to negative 1. In other words, t minus ti is negative. The opposite can be said true for when ti is less than t. So if we have t here, we have t1, for example, that's less than t, and so we've got a value of 1 in the function. This sine function is going to help us to determine whether we have to accumulate payments or we have to discount payments. So let's have a look here. We can say in general, and we're saying in a general sense, that the value of a cash flow xi paid at time ti at time t, so the value at time t using a simple interest rate r is given by this very interesting looking formula here. So what we have to a degree is we're taking the absolute value between the difference, or the absolute value of the difference between the valuation date and any point in time. So that just makes sure that we find the absolute value between the difference in time points. So we're not having negative r times time or something like that. It's ensuring that whether we select time t2 or time tn or whatever it is, each time we're recording something positive in the factor. However, where we do see the discounting get involved is when we've got this sine of t minus ti. See here, this takes, again, value of negative 1. You can see it here, negative 1 when ti is greater than or equal to t. And that's simply stating that if we are in the case where ti is greater than t, we need to discount backwards to time t. But equivalently, if we're standing in time where the ti is less than the focal date, then we actually have to accumulate to time t. And the last thing you should notice is, instead of putting absolute signs here, I've actually changed it to just normal expressions. Sorry, just expressions in brackets. So for the case where ti is greater than or equal to t, the absolute value of t minus ti is actually the negative of what's inside the function. It's ti minus t, right? Because when ti is bigger than t, we get a positive difference between ti and t. But when ti is less than t, then we have to take the original function in the absolute value sign. We're taking t minus ti, because again, t minus ti in this case will be positive. So we're getting both positive values in these two expressions. So now that we've found it for one payment, we can actually find the total value of the set of payments, x1, x2, all the way to xn. And that's simply equal to the sum of all the payments from I equals 1 to n of all these particular payments. Again, we've used some summation notation here. And yes, this perhaps may be slightly complicated, but it does generalize a problem, or it does generalize how to find the value of a series of cash flows at a particular time using a particular interest rate, which is why I like it. It's a very generalized formula that can help you on your ways. Now, of course, what we want to do is we want to find equivalent sets of payments. So let's suppose we had two sets of payments, x1, x2, all the way to xn, occurring at time 1, time 2, and time n. But now we have a second set of payments. Notice there are now m payments, and we've labeled them as y1, y2, all the way up to ym. Doesn't necessarily mean that they're the same number of payments. In fact, there could only be one payment in this list. But again, this is a very generic, generalized formula. And these occur at times tau 1, tau 2, and tau m. Very similar situation. And again, we're going to say, well, tau I and ti and tau I are both elements in R. They can be negative, they can be positive. And we can represent this set of payments here. So again, looks like a very similar diagram that we had on the previous page. We've got our x values. We've also got our y payments. They do look like they align with one another. I should note that this is just for it's for the purposes of showing a diagram. These aren't necessarily to scale or anything of those sorts. Doesn't necessarily mean that they're aligned. Tm or tau m is not necessarily aligned with Tn. It's just for visual depiction. So, if we are to state that they are equivalent to one another, then equivalently what we could simply do is say, well, we know what the value of the payments at x are at time t. Here's the expression we derived previously. And so equivalently, we could just apply the same formula, except we replace our xi with our yi and our ti with our tau I. And so these two sets of payments are equivalent if this follows true. They're equal to one another. And that is, in some sense, the mathematical equivalent of the statement we had on the previous page. If you remember here, is that we say two sets of payments are equivalent at a given simple interest rate if dated values of any set at a common date, t, are equal. And so that's the formalization of that formula. So let's have a look at a particular example of this. Let's say Samuel owes Jessica $700 due in 3 months and $300 due in 6 months' time. Let's say Jessica accepts $400 now. How much will Samuel be required to pay at the end of 1 year, provided they agree on a simple interest rate of 10% and a focal date at the end of 1 year? So, let's draw in what's happening here. We've got our $400 that Samuel has paid to Jessica now. I've put this in light blue. Samuel's also going to pay Jessica a sum of money, X dollars, at 12 months. Notice here I've put 12 in a different color to denote that it is in fact the focal date. Now, we've also been told in the question that the other set of payments, the equivalent set of payments to $400 now and some sum of money in the future, is the equivalent of $700 due at time 3 and $300 due at time 6. So what we have to do is find the value of x so that the discount, or the value of x plus the value of the 400 is the same as the value of the 700 and the value of the 300, all at time 12. So the first thing to note, I guess, in this example is to say, well, the 400 is 12 months. The $400 that gets paid now is 12 months in the past of the focal date of 12. The $700 is 9 months in the past of the focal date. The 300 is, 6 months in the past of the focal date, not 3. And so when we, that should be 6 months there, it follows that we can use the same, or that formula that we use, that generalized formula, where we take x. Now, x is at the focal date, and therefore at the focal date it has value x. But the $400 doesn't have value $400. It has value 400 plus 1 plus r, which is 0.1, times 12 over 12. That's the 12 months accumulation. Then on the other side, of the flip side of the equation, we've got the $700, which we need to accumulate by 9 months here. So we've got 0.1 times 9 over 12. And then finally, we've got the $300, which we need to accumulate, and correctly I've written in the equation 6 on 12 months into the future. And again, multiply that by the simple interest rate of 10%. Now, if I calculate all these values, this gives me x plus 440 is equal to 752.5 plus 315. And then we can solve or do some algebraic manipulation to subtract 440 from both sides. And this leaves me with an x value of 627.50. So in other words, Samuel's going to pay $400 now and $627.5 in 1 year's time. Let's take a look at a final example here. And this final example is actually going to deal with dates. So on the 5th of February 2020, a person borrowed $5,000 at 12%. He paid $500 on the 10th of April, $1,000 on the 15th of May, and $2,000 on the 20th of June 2020. What is the balance due on the 25th of August 2020? So, we're going to look at this from the perspective again of a timeline here. And we're simply going to state, or we're going to put in all the information we have. We know 5th of February, $5,000. It's borrowed. I've put it in a dark blue color to denote that this is the one set of payments. The other set of payments is in fact equal to the remaining payments in the question, because in 10th of April we know that he pays $500. 15th of May he's paying $1,000. 20th of June $2,000, and finally the balance amount, or equivalently you could think of the balance amount as the final payment, so that it is equivalent to $5,000, is the 25th of August 2020. Notice here that the 25th of August is again in green because it's the focal date. So the first thing to note is we are in a leap year, so 2020, which means if you were to calculate it between how many days there are between the 5th of February and the 25th of August, there are 202. There are 137 days between April 10th and August 25th, 102 days between 15th of May and 25th of August, and finally there are 76 days between 20th of June and 20th of June and 25th of August. So again, I'm just going to put that diagram up for us. And again, what we're going to have to do is we're going to have to accumulate all the payments because they are payments in the past. So we're going to have to accumulate them all to the current focal date. And we do it as such. We've got our X amount. So we're going to look at the light blue values first. We've got our X. We've got our 500. Our 500 is occurring sometime in the past. We need to accumulate this by 137 days because it's 137 days into the past. Divide that by 365. Now, you might be saying, hold on a second, I thought this was a leap year. We need to divide that by 366. Yes, while that might be the intuitive case, unfortunately, the convention is that we always use 365 days, irrespective if it's a leap year or not. But we do, however, include the extra day that is part of the leap year in the numerator, just not in the denominator. So by convention, what we have is 0.12%, which is the interest rate, times 137.0365. Then we've got the $1,000 payment, which is occurring at 15th of May. We're accumulating that same interest rate, but now by 102 days. This other payment of $2,000 gets accumulated by 76 days. And finally, that is equivalent to the individual payment or the individual loan amount that's big at the very beginning of $5,000, and that's accumulated by 202 days. So once we calculate all that using a calculator, we get the following sums. After some algebraic manipulation, we get a value that X is equal to 172.6.03. And it's here that we've finished the example. What I should point out is that in a simple interest context, the value that you get, or the value of the missing payment that you get, is actually dependent on the focal date itself. So if, for example, I were to make the 20th of June the focal date, you'd find that the value of X is very much in the similar ballpark to the value that we just got now, but it's still slightly different and not equal to the 12726.03. So it's important to make sure that you express everything in terms of the focal date, especially for simple interest calculations. That might not be necessary, and we'll find out later on that the focal date or that the value of the missing payment doesn't necessarily have as much dependency on the focal date when we're dealing with compound interest.